Leah here from leahforsci.com/MCAT, and in this video we'll talk about force, equilibrium, and free body diagrams in preparation for the MCAT. Now I teach this topic with caution because free body diagrams can be very time consuming, and on the MCAT you don't have that kind of time. So instead I'll show you what to do, and I want you to utilize this in practice, but when it comes to your practice exams and your real exam, I want you to try to simplify this as much as possible so that you don't waste any time. When we're dealing with equilibrium, you'll often see an object that isn't moving or does not have a net force in any direction. You can call this object at equilibrium to imply that the forces in the different directions are all equal or they all cancel out. But there are different types of equilibrium to consider. Translational equilibrium has to do with motion. So that means if you have an object that has a force in one direction and it would be moving, but then you have a force in the other direction canceling it out, that's considered translational equilibrium. But that means the object doesn't have a net force. It doesn't necessarily mean that the object is stationary. Let's use a simple block where the downward force is gravity and the upward force is the normal force. This block is not moving in the y direction because it is in equilibrium, meaning the upward force and the downward force perfectly cancel out, or simply the sum of the forces in the y direction are equal to 0. But now, for example, if the block is moving to the right or the left with a constant velocity, that means the change in velocity is equal to 0, and change in velocity over time is equal to acceleration. So if delta v over t is 0, then F equals ma, a is 0, the force is 0, this object is still in equilibrium, but this is considered dynamic equilibrium. It doesn't have a net force, it still has a constant velocity and is moving. To say that an object is not moving at all, that's when you want to talk about static equilibrium, where you have the constant velocity of 0, it's static, it's not moving. When setting up these equilibrium equations, it helps if you omit the signs, for example, the positives and negatives, and instead just think of what the sign implies so you have a logical diagram. Because the signs can confuse you, but the logic behind the signs will help you with your drawing. A standard free body diagram is basically taking your object out of the story, out of the question, and just drawing arrows to represent the different forces acting on this object. I like to draw free body diagrams with either a square, a block, or a dot. And this block can represent anything from a person to a car to a hammock. Any object is easier to draw as a block than trying to waste time drawing pictures, especially if we're not artists, because this is a science topic, not art. Now, regardless of the size of this object, unless you're specifically being tested on center of mass or center of gravity, assume that the entire mass of the object is concentrated in the center of the block or the dot that you're drawing. And that means all the forces can come out of that one object instead of having to figure out where to draw it on a complex item. Say this block is resting on a table, we'll show that the downward force is the force of gravity, or mass times the acceleration of gravity. The upward force is the normal force, because the normal force applies to any object resting on a surface. Now let's say the wind is attempting to force the block to the right. We would draw an arrow to the right and call this force of the wind, and you can put whatever subscript you want under the F, as long as you know what you're referring to. Now, some of these are common: Fn, normal force; Fg, gravity. But in the last video, we wrote Fp, the force of a person; Fw, the force of a wall. As long as you know what you're talking about, you're fine. But now let's say the block isn't moving despite the wind trying to push it. We can show that the force of friction is countering the force of the wind. Now, this object here is in equilibrium. So all you do is set these equal to each other, regardless of positive or negative, and let me show you how that works out. If I tell you that the block has no motion or acceleration in the x direction, we can assume that the sum of the forces in the x direction is equal to 0, and since the forces are force of friction and wind in the opposite direction, we can say that the force of friction equals force of the wind. This is without using any positives or negatives, just logically saying if one is to the right and one is to the left, they're opposite, and therefore they are equal to each other if there's no motion. If you want to get technical, you can set it up as the sum of the forces in the x direction equals 0, which is equal to positive for the right, so that's going to be force of the wind, negative for the left, force of friction, and when you solve it, you'll actually get the same equation we wrote earlier, but jumping straight to the setup that doesn't have any signs is faster if you understand how to set this up. Now we can do the same thing for the y direction. We know the block isn't moving, so the sum of the forces in the y direction are equal to 0. The upward force is force normal, and I write Fn so as not to confuse it with a capital N for newtons. The upward force is force normal, the downward force is force gravity. They are equal and opposite to each other, so we set them equal to each other. That's the fast way. Now let's show it the other way. If the sum of the forces in the y direction is equal to 0, that is equal to the normal force upward, positive, minus the gravitational force downward, so that's negative. And once again, if we rewrite this equation, we get what we already have. Now imagine we have the same block sitting on a frozen lake that has a low amount of friction, so that the force of the wind still cancels the force of friction, but there is a net velocity on the object. So let's say there was a strong gust of wind and the object started moving, and then friction opposes it just enough to cancel out any acceleration, but the block is still moving at a constant velocity. The block is still in translational equilibrium, in this case dynamic equilibrium. We can still set up the free body diagram because the sum of the forces equals 0, even though it's moving at a constant velocity. Other free body diagrams that you may see is, let's say this block now represents a toy wagon, and you have a kid pulling it at some angle theta. So that'll be your angle theta. If it's being pushed or pulled at an angle, the way you set it up is going to be the same. But if the force is now in a slightly upward direction, you're dealing with something between the x and y components, and you want to break it up so that you can clearly see what's happening in the x and what's happening in the y direction. Down, still force of gravity. Up, still the normal force. But now we have an additional component to add in the y direction. If we take that force, either a push or a pull, at an angle, we have to break that up into the force x and the force y using trigonometry. And now when you set up the equation, you'll have the sum of the forces in the y direction is going to be the force applied, or the green force, positive, the normal force, positive, and the gravitational force, negative. And that's still equal to 0 because the block isn't moving up or down. But now when you set up the x direction, you can say the sum of the forces in the x direction, let's call this F applied x, so FAX, is going to be positive FAX, which you would set up as F applied cosine of theta. And then if you have friction, you'd set that up in the opposite direction. If you don't have friction, then you have F of x equals mass times acceleration. The scary free body diagram for most students is the inclined plane. And that's because we're dealing with an object that is not sitting on the x or y axes, but rather somewhere in between. Now I break this down in detail in the trigonometry video, which you can find on my website at layerforsci.com/MCATmath, and that's where you'll see exactly why I'm about to do what I do. Now I'll just give you the overview. All we do is switch the axes so that x is at an angle but parallel to the inclined plane, and y is also at an angle but perpendicular to the inclined plane. In the trigonometry video, I proved to you why, given an angle theta, x is going to use sine rather than cosine, and y will use cosine rather than sine, but everything else is still the same. Gravity does not change just because the incline changes, and so gravity goes straight down. If gravity goes straight down and it's in between the x and y components, you have to break it up so that your force of gravity in the x direction is going to be sine of your angle, and force of gravity in the y direction is going to be cosine of the angle. Now we don't care about force of gravity in the y direction, we do care about the normal force, which is equal to mass times gravity in the y direction. That's where we care about the cosine component. And if you have friction, that goes in the opposite direction to the x component. Another confusing factor here is when to use positive and when to use negative. Don't worry about the signs that you're given, turn every sign into something logical. So for example, gravity is a negative acceleration because it goes downward. Don't worry about the negative. Gravity in this case goes to the left. Friction is negative because it opposes the direction of motion. But in this case, friction is towards the right, so if I try to use negative, it'll be very confusing. Now, if I tell you that this block is not sliding down the inclined plane, then I can assume that the sum of the forces in the x direction are equal to 0. If the sum of the forces in the x direction equals to 0, then I can say that force of gravity in the x direction is equal to the force of friction, and I don't have to worry about which one is negative or positive, because again, this is where it gets confusing. Instead, in this case, gravity goes to the left because the way the inclined plane is drawn, it goes left. Friction goes to the right, so don't worry about your negatives and positives and just set it up this way. If you do have to set up a more complex equation, pick one and stick with it. As long as you're consistent, it'll work out. I can choose this to be negative and this to be positive, making the gravitational acceleration negative but the friction positive. And then you typically want to choose positive y upward and negative y downward, once again, setting those equal to each other. Notice here that the normal force is mg with a component of gravity, so that's mg cosine of theta, which perfectly balances the force of gravity downward, setting the sum of the forces of y equal to 0. Again, for a breakdown of why we use sine and cosine opposite to the normal convention, be sure to see the trigonometry video where I explain it in detail. Don't take that explanation as something you have to apply each time, but it needs to be intuitive so that you don't waste time being confused on this. Let's do one more free body diagram. Imagine we have a hammock suspended from 2 trees. That'll be the hammock. And we have a student here laying in the shade studying for his MCAT. If you want to calculate the sum of the forces here, the first thing you want to do is turn this entire system into one point. If you take the time to draw the tree and the hammock on the MCAT, you're wasting too much time. Here we have tree 1, tree 2. Here we have the student with the hammock as a dot, and here we have the ropes that support the hammock. Let's make this bigger so we can mark it up. And once again, we set about with the sum of the forces. Downward, we have the force of gravity, the student and the hammock. Upward, in this case, we have not the normal force, but the force of tension in the ropes that support the hammock. We have 2 ropes sitting at some angle between the x and y component, and so we have to break them up into their vectors. Assuming the ropes are at the same angle, the sum of the forces in the x direction equals 0, because the hammock isn't moving. That means the tension to the x of one rope equals and balances the tension x in the other rope. We can simply call this positive x and negative x, assume they cancel out, and don't even worry about the math. But the tension in the y direction can get tricky. The sum of the forces in the y direction equals 0, and you can set it up as force of gravity is equal to 2 times tension in the y direction. The reason it's 2 is because half of it goes to one rope and half of it goes to the other rope, and obviously you'll find this using the angles given in trigonometry. But don't worry, we'll tackle tension by itself in its own video. You can find my entire series on MCAT forces along with the cheat sheet and practice quiz by visiting my website layerforsci.com/forces. Are you stuck on a specific MCAT topic? I offer private online tutoring where I focus on your needs to strengthen your individual weaknesses. Tutoring details can be found using the link below or by visiting my website layerforsci.com/MCAT-tutor. Are you overwhelmed by the sheer volume of information required for the MCAT? Are you worried that lack of a proper study plan and low MCAT score will prevent you from getting into medical school? My new ebook, The MCAT Exam Strategy, a 6-week guide to crushing the MCAT, will help you formulate a concrete study plan by helping you figure out where you stand now, identify your goals, and figure out what it takes to reach them. And it's yours free when you sign up for my email newsletter at MCATexamstrategy.com. By signing up for my email newsletter, you'll also be the first to know when I have new videos, MCAT study guides, cheat sheets, tips, and so much more. The link again, MCATexamstrategy.com.